Welcome to Tell Me More Stories Told as Podcast. Get ready for an adventure, a journey to the ultimate frontier, the incredibly small. Forget everything you think you know for a moment, because we're diving deep into the amazing story of the atom, the fundamental building block of, well, everything.
That's right. It's a quest, really. For thousands of years, thinkers have pondered what the world around us is truly made of.
Exactly.
Today, we're going to explore that quest, a scientific detective story spanning millennia, filled with brilliant minds, unexpected discoveries, and, well, a constant reshaping of our understanding.
Yeah, the sources paint such a vivid picture of this whole intellectual adventure.
They really do.
And it blows my mind that the idea of these tiny fundamental particles goes all the way back to ancient Greece.
Right. Atomos.
Yeah, they even had a word for it, atomos, meaning uncuttable. Imagine without any of our modern tech, they were already thinking about matter as being made of these indivisible pieces.
It was pure philosophical brilliance, really. A mental leap.
Yeah.
Not based on experiments, like you said, but
But isn't it wild that the very name we use today has its roots in that ancient idea? It's amazing.
it's a testament to, human curiosity. That early philosophical seed eventually grew into a scientific revolution.
Okay, so when did it shift from philosophy to actual science?
Well, a real turning point came in the early 1800s with John Dalton. He wasn't just thinking about it, he was actually measuring how elements combine in chemical reactions.
Okay, let's unpack this. Dalton's big insight came from what's called the law of multiple proportions. Now, that might sound complicated,
That does sound a bit complex, yeah.
but it's actually a beautifully simple idea, right? He noticed that when two elements form different compounds, the weights of one element that combine with a fixed weight of the other always show up in simple whole number ratios.
Exactly. Think about it like this.
Mm.
Your source mentioned tin oxides. Dalton found that for a certain amount of tin, one compound had a specific amount of oxygen, and another had exactly double that amount of oxygen. That 1.2 ratio screamed that these elements were combining in discrete packets, these atoms, and that each element had a unique weight.
And he saw this elsewhere too, right? Not just tin.
Oh, yeah. He saw similar patterns with iron oxides, nitrogen oxides.
Mm-hmm.
It really made his argument compelling. It was the first real, scientific evidence for the atomic theory.
So it's like he was discovering the hidden rules of how these fundamental particles fit together just by carefully weighing things.
Precisely. Like finding the invisible Lego bricks of the universe.
Wow. But the story doesn't stop there, does it? Because the idea of the atom as this solid, uncuttable thing didn't last.
Not at all. Here's where things get really interesting. Fast forward to 1897, and along comes J.J. Thomson.
Thomson, cathode rays.
Exactly. His experiments with cathode rays, these mysterious beams of light in vacuum tubes, led to an electrifying discovery. Literally. The electron.
And this was a game changer, right? Because these electrons, they were found to be negatively charged particles and incredibly tiny.
Way, way smaller and lighter than even the smallest atom, hydrogen.
So that instantly proved that atoms weren't indivisible after all. There were smaller things inside. It just shattered that ancient Greek idea.
Completely. Thomson then proposed what's often called the plum pudding model.
Right, the plum pudding. Can you describe that?
Sure. Picture a sphere of positive charge, like a blob of, pudding,
Okay.
with these negatively charged electrons scattered throughout it, like plums. It was his way of explaining how the atom could be electrically neutral overall,
So from being uncuttable for millennia to suddenly having these tiny bits floating around inside, that's a massive shift in our understanding of reality.
Huge shift. But the plum pudding model itself didn't stick around for too long, did it?
No, it seems like these models kept getting updated pretty quickly.
They did. It was a stepping stone. What's fascinating about science is how one idea leads to another, and new experiments can challenge and refine or even completely overturn existing models.
Like what happened next?
Well, in the early 1900s, Ernest Rutherford and his team conducted a series of groundbreaking experiments. They fired tiny positively charged particles, called alpha particles, at incredibly thin sheets of gold foil.
Okay, gold foil. And the expectation, based on Thomson's plum pudding model, was that these alpha particles would mostly just pass straight through, right? Maybe with a slight nudge here and there.
Exactly, like shooting tiny marbles at something soft, like pudding.
But that's not what happened.
Not even close. What they actually saw was utterly astonishing. A tiny fraction of those alpha particles were deflected at very large angles. Some even bounced straight back.
Straight back? How is that even possible?
Rutherford famously said it was as surprising as if you fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you.
Wow. That really paints a picture. So what did this completely unexpected result tell them about the atom?
It forced Rutherford to come up with a completely different picture. He realized that for those alpha particles to be deflected so violently, there had to be a tiny, incredibly dense center of positive charge containing most of the atom's mass.
And that's the nucleus.
That's the nucleus. He called it the nucleus.
Mm.
The electrons, he proposed, orbited this nucleus-like planets around a star in a vast, mostly empty space.
So most of the atom is just empty space.
Pretty much. It was a truly revolutionary vision of the atom.
Okay, this is where it gets really interesting. So now we have a tiny, positively charged nucleus and electrons zipping around it in this mostly empty space. But this model brought up a new problem, didn't it?
It certainly did.
According to the physics of the time, these orbiting electrons should be constantly losing energy, like radiating it away.
Right.
And spiraling into the nucleus, right?
That's exactly what classical physics predicted. The atom should collapse in a fraction of a second.
So why didn't all atoms just collapse? That's a huge question.
It's a crucial question, and it stumped scientists for a while. Then, in 1913, Niels Bohr offered another pivotal idea.
Bohr! Okay, what was his solution?
He proposed that electrons could only exist in specific quantized energy levels or orbits around the nucleus, almost like set tracks.
Quantized, meaning only certain specific energy values allowed.
Exactly. They couldn't just be anywhere. And they could jump between these orbits by absorbing or emitting energy in the form of photons, tiny packets of light.
Ah, photons. And this explained
why atoms only emitted and absorbed light at the specific wavelengths, creating those unique spectral fingerprints we see. Each element has its own signature.
So it was like the electrons were restricted to certain lanes or tracks around the nucleus, and they could jump between them but couldn't exist anywhere in between.
That's a good analogy, yeah.
And this solved the stability problem.
Well, it worked brilliantly for the hydrogen atom, the simplest one. It explained its spectrum perfectly.
Not for more complex atoms.
It had its limitations, yes. It didn't fully explain the behavior of atoms with more than one electron. Bohr's model wasn't the final word, but it was a vital step forward, introducing quantum ideas into atomic structure.
Okay, so the picture is getting more complex. We have the nucleus, these specific electron orbits. What came next?
Well, scientists kept digging deeper. In the years that followed, more pieces of the atomic puzzle fell into place. In 1919, Rutherford himself identified the proton.
The proton, the source of the positive charge in the nucleus.
Precisely. A positively charged particle residing in the nucleus. So now we have positively charged protons in the nucleus and negatively charged electrons orbiting.
But there was still something missing, right? Because the atomic weights of elements didn't quite add up based on just the number of protons. They were heavier than expected.
Exactly. The masses didn't make sense. Rutherford predicted the existence of another particle within the nucleus, one with no electric charge.
Ah, neutral.
But with a mass similar to that of the proton. This elusive neutral particle, the neutron, was finally discovered by James Chadwick in 1932.
The neutron. Okay, so 1932. And with that discovery, we finally had the main cast of characters in our atomic story. The nucleus, home to protons and neutrons, surrounded by a cloud of electrons. It's incredible to trace how this understanding unfolded, each new discovery building upon or challenging the previous ideas.
Absolutely. But even this seemingly complete picture continued to evolve. By the 1920s, the revolutionary ideas of quantum mechanics began to provide a much more nuanced
and frankly mind-bending view.
Definitely mind-bending, a new view of the atom, especially concerning the behavior of those electrons.
Okay, now we're venturing into the realm of things that get a little, well, weird, right? Heisenberg's uncertainty principle and Schrödinger's wave equation, these aren't exactly concepts we encounter walking down the street.
They're not, no. But they are absolutely fundamental to our modern understanding. Quantum mechanics revealed that electrons don't just orbit the nucleus in neat, predictable paths like tiny planets. That Bohr model was just an approximation.
So no neat orbits? What then?
Instead, they exist in probability zones called orbitals. Think of them as regions of space where there's a high likelihood of finding an electron with a certain amount of energy. Probability zones. So like fuzzy clouds.
Kind of, yeah. Instead of knowing exactly where an electron is at any given moment, we're dealing with probabilities, with these fuzzy clouds of where it might be. It's a far cry from those simple orbital diagrams we often see.
That sounds very uncertain.
Well, that brings us to Heisenberg's uncertainty principle. It tells us that there's a fundamental limit to how accurately we can simultaneously know both the position and the momentum, which includes speed and direction, of an electron.
So you can know one well, but not the other.
The more precisely we measure one, the less precisely we can know the other. It's a fundamental property of nature at this scale.
In Schrödinger's equation.
Schrödinger's wave equation, on the other hand, describes the electron mathematically as a wave. And those orbitals we mentioned, they're basically mathematical solutions to that equation, representing those probability distributions. So the electron is both a particle and a wave.
It behaves like both, depending on how you measure it. It exists in this blurry realm of possibilities until we interact with it.
It's a real shift in perspective from thinking of electrons as tiny marbles to these wave-like entities existing in these probabilistic clouds. Definitely something that makes you think.
It really does. Now, let's zoom in on those subatomic particles a little more. We've got electrons, negatively charged and incredibly light.
Check.
Protons, positively charged and much more massive, residing in the nucleus.
Check.
And neutrons, neutral in charge, with a mass just a tiny bit greater than protons, also in the nucleus.
Okay, the main three.
And here's a fun fact for you. If an atom were blown up to the size of a football stadium, the nucleus would be about the size of a single pea in the center.
No way. Just a pea.
Just a pea. That really shows you how much empty space there is inside an atom. Almost all of it.
Wow, that pea in a stadium analogy really puts the scale into perspective. And it's the number of protons that truly defines what element an atom is, right? That determines if it's hydrogen or helium or carbon.
Exactly. That's the atomic number. 1 proton is hydrogen, 6 protons is carbon, 8 is oxygen, and so on. That number dictates its chemical identity.
Okay. Now things get a bit more varied with neutrons, you mentioned.
That's right. Atoms of the same element can have different numbers of neutrons. These are called isotopes.
Isotopes, so same element, different weight.
Precisely. They behave chemically the same because they have the same number of protons and electrons, which determine chemical bonding. But they have different atomic masses because of the varying number of neutrons. Think carbon-12 versus carbon-14.
Ah, right. Carbon-14 dating uses that difference.
Exactly. And it's mind-boggling to think that even these fundamental particles, protons and neutrons, aren't the smallest things out there, are they?
Wait, there's more. Smaller than protons and neutrons?
Oh, yes. They're actually made up of even tinier particles called quarks.
Quarks? Seriously?
Yep. In the standard model of particle physics, electrons are considered truly fundamental, or elementary, with no known internal structure, as far as we know.
Okay.
But protons and neutrons are composite particles. A proton is made of 2 up quarks and 1 down quark.
2 ups, 1 down for a proton?
And a neutron has 1 up quark and 2 down quarks.
Okay. 1 up, 2 down for a neutron. And what holds these quarks together?
They're held together by an incredibly strong force, appropriately named the strong nuclear force, which is mediated by particles called gluons.
Gluons, like glue.
Exactly like glue, but much, much stronger. It's like discovering another layer of reality within what we thought were the basics.
It's like peeling back the layers of an onion. You think you've reached the core, and then you find another layer. Now, speaking of the nucleus, even though it's incredibly tiny compared to the overall size of the atom...
That pea in the stadium.
Right. It contains virtually all of its mass, over 99.99994%.
It's astonishing. It's like that pea holding almost all the weight of the entire stadium.
So what keeps all those positively charged protons crammed together in such a 20 space? They should repel each other like crazy, right? Positive charges push apart.
They do. That's the electromagnetic force trying to push them apart.
Yeah.
But there's another force at play, the strong nuclear force we just mentioned.
The one holding quarks together.
That same force, but it also acts between protons and neutrons. It's incredibly powerful, but operates only over very short distances, essentially within the nucleus. It overcomes the electrical repulsion between the protons and binds the nucleus together.
So it's like super glue for the nucleus.
A very good analogy. And the balance between the number of protons and neutrons is crucial for the stability of the nucleus. Some isotopes have an unstable balance.
And those are the radioactive ones.
Exactly. They undergo radioactive decay to try and reach a more stable configuration.
Now, let's turn our attention back to the electrons. They exist in that cloud surrounding the nucleus.
Right, held there by the electromagnetic force, the attraction between the negative electrons and the positive protons in the nucleus.
And we talked about orbitals as those probability zones, each corresponding to a specific energy level.
Correct, like shelves where electrons can sit, but only specific shelves are allowed.
And electrons can jump between these energy levels, these shelves, by absorbing or emitting photons, those packets of light we mentioned earlier.
Precisely. If an electron absorbs a photon with just the right amount of energy, it leads to a higher energy level, a higher shelf.
Okay.
When it falls back down to a lower level, it emits a photon with an energy equal to the difference between those levels.
And that emission of photons at specific energies, that's the element's fingerprint.
That's its unique spectral fingerprint. It's like every atom has its own barcode written in light. Different jumps correspond to different colors or wavelengths of light.
And these spectral lines aren't just pretty colors we see through a prism, are they? They're incredibly useful tools for scientists.
Oh, absolutely invaluable. By analyzing the light emitted or absorbed by a substance, we can determine its exact atomic composition.
Even from far away.
Even from millions of light years away. This technique, spectroscopy, is how we know what stars are made of.
Wow. And didn't you mention something about helium earlier?
Yes, a fantastic example. Helium was first discovered by observing its unique spectral lines in the light from the sun during an eclipse in 1868.
So they saw its light signature from the sun.
Before it was ever isolated and identified chemically here on Earth, which happened years later. Talk about solving a cosmic mystery from our own backyard.
That's an incredible story, discovered in the stars before we even knew it was here. If you're enjoying these kinds of stories and deep dives into science, make sure to hit that subscribe button for Tell Me More Stories Told as podcasts so you don't miss our future explorations.
Definitely worth subscribing. Now, we touched on isotopes earlier, atoms of the same element with different numbers of neutrons.
Right. Some are stable,
Their nuclei content to remain as they are indefinitely.
while others are radioactive, spontaneously transforming over time.
And this radioactive decay can take several forms. Alpha decay, where a nucleus emits an alpha particle, which is basically a helium nucleus, 2 protons, 2 neutrons.
Okay.
Beta decay, where a neutron turns into a proton, emitting an electron and an antineutrino, or vice versa.
Changing the element itself in that case?
Yes, beta decay changes the atomic number. And then there's gamma decay, which often accompanies alpha or beta decay. That's when the nucleus releases excess energy in the form of a high-energy photon, a gamma ray, without changing its proton or neutron count. It's just settling down.
And each radioactive isotope has its own characteristic decay rate, right? The half-life.
Exactly. The half-life is the amount of time it takes for half of the atoms in a sample to decay. It can range from fractions of a second to billions of years. It's like a natural, predictable ticking clock within the atom.
Now, here's an interesting tidbit I came across in the sources. Out of all the stable atoms we know, only 4 have both an odd number of protons and an odd number of neutrons in their nucleus. 4. That seems surprisingly rare.
It is surprisingly rare. Those are hydrogen-2, deuterium, lithium-6, boron-10, and nitrogen-14. Most stable nuclei prefer to have even numbers of protons and/or even numbers of neutrons.
Why is that?
It has to do with the way nucleons, protons, and neutrons pair up within the nucleus due to spin interactions. Pairs of protons and pairs of neutrons lead to greater stability. It's energetically more favorable. Odd nuclei are generally less stable.
Interesting. Like they prefer to have partners.
Yeah.
Okay, let's talk about size and mass again for a moment. Atoms are incredibly tiny, measured in picometers, trillionths of a meter.
Almost impossible to visualize how small.
And as we've said, almost all the mass is crammed into that minuscule nucleus. Atomic mass is often measured in Daltons or atomic mass units.
Right, where 1 Dalton is roughly the mass of a single proton or neutron. Hydrogen's about 1 Dalton. Carbon-12 is exactly 12 Daltons by definition.
And to really grasp how small atoms are, I read somewhere that a human hair is about 1 million carbon atoms wide.
Something like that, yeah. Or consider this. A single grain of sand contains more atoms than there are stars in the observable universe.
That really puts the incredibly small into perspective. It's just mind-boggling numbers.
Completely. And atoms don't really have a sharp edge either, do they? That electron cloud just kind of fades out.
Yeah, the probability just gets lower and lower further out, but never technically reaches 0. It's fuzzy.
Exactly.
We also have this concept of magnetic moment. Both electrons and the nucleus have this intrinsic property called spin.
Which isn't exactly like a spinning top, but it's a fundamental quantum property that behaves like angular momentum.
And the spin generates a tiny magnetic field.
Precisely. It contributes to the atom's overall magnetic moment. The way these tiny magnets align, or donor line, within a material determines its bulk magnetic properties, why iron is ferromagnetic and wood isn't. It all comes down to the electrons.
Okay, that makes sense. Now, valence electrons, those are the electrons hanging out in the outermost shell or highest energy levels of an atom.
The frontier electrons.
Right. They're the social butterflies of the atomic world, responsible for how atoms interact and form chemical bonds, right?
Absolutely. Atoms are always trying to achieve a stable, filled outer electron shell, like the noble gases helium, neon, argon, etc.
The noble gases are famously unreactive, kind of aloof.
Because their outer shells are already full. They're stable and happy on their own. Other atoms react, share, gain, or lose electrons to try and achieve that same stable configuration. This drive for stability through their valence electrons is the foundation of all chemistry.
How everything sticks together to form molecules and materials.
Exactly.
And atoms don't just exist as solitary entities, do they? They come together to form the different states of matter we experience.
Right. Solids, where atoms are locked in a structure, liquids, where they're close but can move around, gases, where they're far apart and zip around freely.
And plasma.
Plasma is often called the fourth state of matter. It's a super hot gas where electrons have been stripped off the atoms, creating a mix of ions and free electrons. Stars are mostly plasma.
And then there's that really weird state at the other extreme, super cold.
The Bose-Einstein condensate, or BEC. At temperatures incredibly close to absolute zero, just billionths of a degree above, some atoms can lose their individual identities and coalesce into a single quantum state.
So they act like one giant atom.
In a way, yes, they behave as a single quantum entity. It's a truly mind-bending state of matter where the weird rules of the quantum world become visible on a macroscopic scale, first created in labs in 1995.
Amazing. So how do we actually see and identify these incredibly tiny atoms? We can't just use a regular light microscope, can we?
No, as we said, the wavelengths of visible light are much larger than atoms, so light just passes around them. But we've developed some incredibly ingenious tools.
Like what?
Well, scanning tunneling microscopes, STMs, can create images of surfaces at the atomic level. They don't see in the traditional sense, but use a tiny probe and a quantum mechanical effect called tunneling to map out the position of individual atoms on a surface.
Wow, so we can essentially image individual atoms now.
On surfaces, yes. We also have mass spectrometers, which are like atomic weighing scales. They ionize atoms and then measure their mass-to-charge ratio very precisely, allowing us to identify the elements and isotopes present in a sample.
And spectroscopy, which we talked about analyzing the light.
Exactly. Analyzing the light they emit or absorb can tell us their identity, even from vast distances across the cosmos. It's like we've developed ways to feel and see something that's fundamentally beyond our normal senses.
It's a testament to human ingenuity, isn't it? Developing tools to probe a realm we can't directly experience. Now, where did all these atoms originally come from? It's a cosmic story, isn't it?
Absolutely. The ultimate origin story. Atoms formed after the Big Bang through a process called nucleosynthesis.
So right after the universe began.
In the first few minutes, yeah.
Ah.
The very early universe was incredibly hot and dense, allowing protons and neutrons to fuse into the lightest elements, mostly hydrogen and helium, with tiny traces of lithium.
So the universe started with just the simple stuff. Where did everything else come from? Carbon, oxygen, iron?
That came much later. Heavier elements were forged in the fiery cores of stars through nuclear fusion. Stars are element factories.
Fusing hydrogen into helium, helium into carbon, and so on.
Exactly. And even heavier elements, beyond iron, are primarily created in the cataclysmic explosions of massive stars, supernovae, and also in the mergers of neutron stars, which are incredibly energetic events.
So as Carl Sagan famously said, we are all star stuff. The atoms in our bodies were literally forged inside stars that lived and died billions of years ago.
It's a profound thought, isn't it? We are intimately connected to the cosmos.
And it's astonishing to think about the sheer number of atoms out there. The sources mention that the Earth alone contains approximately 1.33 by 10,050 atoms.
Yeah, that's a 133 followed by 48 zeros. A number so vast it's almost impossible to truly wrap our heads around.
Just countless. And most of the ordinary matter in our galaxy, the stuff made of atoms, is actually inside stars, often in that plasma state.
That's right. The space between stars, while not perfectly empty, is incredibly diffuse compared to stars and planets.
And while we mostly encounter these ordinary atoms, scientists are also exploring the possibilities of rare and theoretical forms, right?
Definitely. They're pushing the boundaries, creating super heavy elements in particle accelerators, Elements with so many protons and neutrons, they only exist for tiny fractions of a second before decaying.
Trying to find the limits of nuclear stability.
Exactly. And then there are exotic atoms, like replacing an electron with a heavier particle like a muon, or even creating atoms made entirely of antimatter.
Antimatter atoms, like anti-hydrogen.
Yes. Scientists at places like CERN have successfully created and trapped anti-hydrogen atoms, an anti-proton nucleus orbited by an anti-electron, a positron. Studying them helps us understand if antimatter behaves exactly like matter, which is a fundamental question in physics.
Wow, it really feels like the deeper we delve into the atom, the more incredible and mysterious it becomes.
It truly does. From that initial philosophical spark in ancient Greece, that idea of atomos,
To the plum pudding, the nuclear model, Bohr's orbits, and now this complex quantum picture with quarks and gluons and probability clouds.
the story of the atom is a true epic of scientific discovery.
And it's a story that's still being written, isn't it? With new discoveries constantly revealing even more about the fundamental nature of our universe.
Absolutely. Particle physics, nuclear physics, quantum chemistry. The exploration continues.
Absolutely. Well, The Learner, we hope this deep dive into the world of the atom has given you a newfound appreciation for these fundamental building blocks of everything around us.
It's a story packed with aha moments and surprising insights, hopefully without getting too bogged down in overly technical jargon.
Yeah, trying to keep it accessible but deep.
And remember, the pursuit of knowledge is a continuous journey. The universe at its smallest scales still holds countless secrets, and our understanding is constantly being refined. There's always more to learn.
For more incredible adventures into the fascinating stories behind the science that shapes our world, make sure to hit that subscribe button for Tell Me More Stories, told as podcast. Don't miss out on our next exciting deep dive.
And maybe we can leave you with a final provocative thought to ponder.
Ooh, I like those. What have you got?
Well, considering the sheer immensity of the universe and the almost unimaginable number of atoms it contains, and the hints of exotic particles and forces we keep finding, what other fundamental forces or particles or even whole undiscovered realities might be out there still waiting to be discovered?
Yeah.
Perhaps hidden within the seemingly empty spaces between the atoms themselves.
Wow, that's a big question to chew on. What else is lurking in the quantum foam or beyond the standard model?
Exactly.
Yeah.
Something to think about.